Hi, today we're going to talk more about electron dot structures, and specifically we're going to talk about those times when you cannot follow the octet rule. We are going to talk about three exceptions to the octet rule. First, free radicals. Second, those times when you have fewer than 8 electrons, which we call incomplete octets. And then those times when we have more than 8 electrons, which we call expanded octets. First, free radicals. A free radical is any molecule that has an odd number of electrons. And the problem with this is you cannot pair up an odd number of electrons without having an electron left out. So let's look at an example. What we're going to look at here is we're going to look at two different molecules. One that's a quote-unquote normal molecule, the hydroxide ion. This is very common, and it's OH minus. The other is hydroxyl radical, which is the neutral OH. So we're going to draw structures for these. Starting with a hydroxide ion, the total number of valence electrons, oxygen should have 6, hydrogen should have 1, and don't forget this is an ion, it has a negative charge, so we're going to have 1 electron. That means we're going to have 8 total valence electrons. Now let's figure out how many electrons we need to complete the valence shells. Oxygen wants an octet. Hydrogen only can put electrons in its 1s shell, so it only needs 2. So we need 10 total electrons. All right, how many of our electrons are shared? 10 minus 8 is going to be 2, so we have 2 shared electrons, and then the number of bonds we're going to have is 2 divided by 2, which is 1. Let's now draw the structure. We have oxygen, we have hydrogen, we have 1 bond between them. How many unshared electrons do we have? We started with 8 electrons. We used 2, so we have 6 left. Hydrogen is full because it can only hold 2 electrons, so those have to go on oxygen. And don't forget, this is an ion. Let's add on the brackets. Let's put in the charge. And that's our hydroxide ion. Now let's look at the hydroxyl radical. So we're going to start off again by finding the total number of valence electrons. Oxygen has 6, hydrogen has 1, but there's no charge, so that's it. 7 valence electrons. How many electrons do we need to complete the valence shell? This is the same as last time. Oxygen wants 8, hydrogen wants 2, that's 10. How many shared electrons should we have? 10 minus 7 is 3. How many bonds would that be? Oh, 1.5? What the heck does that mean? Well, let's think about this. We can't have a half bond, so maybe it's 1 and maybe it's 2. Let's think about that by drawing. If you get stuck on any sort of things like this, if any of your math seems wrong, just try drawing and using the total number of valence electrons you have as your guide. So oxygen and hydrogen, we have to have at least 1 bond between them because they are connected. Could we put in 2 bonds? Well, we can't. Hydrogen with 2 electrons is full, so it's going to have to stay as 1 bond. Let's fix that. How many unshared electrons do we have? Well, we started with 7. We've used 2 of them. That gives us 5. So let's put those 5 around oxygen. 2, 4, 5. This is not an ion, so we can just put that into our overview slide. And now let's look at the differences. Hydroxide here has both atoms in a noble gas configuration. Hydroxyl radical does not, and there's no way we could rearrange it to do so because we have this unpaired electron. Anytime you have anything with an unpaired electron, which happens anytime you have an odd number of electrons, you're going to end up with a very reactive molecule. That's why they call it a radical. And this is why you don't want free radicals in your cell, because if something like a hydroxyl radical does get produced in your cell, and believe me, your cells do make them, it will react with whatever is closest. And if that closest thing happens to be something like, let's say, your DNA, you could get a mutation. All right, now let's move on to possibility number 2, which is incomplete octets. There are some elements that just won't form octets, and luckily, they are few enough that you can memorize them. Beryllium forms compounds with 4 valence electrons. Boron and aluminum form compounds with 6 valence electrons. Now, why would they do this? Why wouldn't they have an octet? And the answer, quite simply, comes down to formal charge. That this helps with formal charge issues. And that becomes very clear if you actually try drawing a structure for one of these compounds. So let's do that right now. Let's look at boron trifluoride. And let's just go ahead and pretend that it is going to make an octet. And so we'll just assume that it does until we see why forming octets is a bad thing. So total number of valence electrons, boron has 3. Each of our 3 fluorines has 7, so that's 21. And then that adds up to 24 total valence electrons for our molecule. If we want everything to have an octet, boron would want 8. Each of our 3 fluorines would want 8, so that's 24. And that means we need 32 electrons. How many of those electrons would be shared? Well, that would be 32 minus 24, which is 8. And 8 shared electrons means we're going to have 4 bonds. So let's go ahead and draw. Here's our boron. Here are the 3 fluorines. And now let's put in our bonds. 1, 2, 3. Everything has to have at least 1 bond between it. Now we need a 4th bond. And so that's going to have to go between a boron and one of the fluorines. And I'm just going to pick this one randomly. And now let's distribute our unshared electrons. We started with 24. We've used 8 of them, so we have 16 left. The left and the right fluorines each have 2 shared electrons, which means they need 6 more each. 2, 4, 6, and 2, 4, 6. And then the double bonded fluorine has 4 shared electrons, so it needs 4 more to have an octet. 6, 6, and 4 gives us 16. So we have used all of our unshared electrons. So this would be the end, but let's check our formal charges. This fluorine right here has 6 unshared electrons and 1 shared electron, 7 electrons. And fluorine normally has 7 valence electrons, so 7 minus 7 gives us a formal charge of 0. This fluorine on the right has the same electron configuration, so no need to do the math twice. It's exactly the same. The double bonded fluorine has 4 unshared electrons and 2 shared electrons, and normally has 7. So 7 minus 6 is going to give us a +1 formal charge for fluorine. Boron normally has 3 electrons. It has 4 shared electrons, so that gives it a -1 charge. And now let's stop and think about this a moment. Not all of our charges are 0. And I'm just going to say, if that rule ends up being broken, it's normally not the end of the world. But now let's look at where our non-zero formal charges are. Our -1 formal charge is on boron, the least electronegative atom. And the +1 charge is on fluorine, the most electronegative atom. By the way, it's not just the most electronegative atom in this molecule, it is the most electronegative element there is. So for fluorine to take a +1 charge, that's just not very stable. So what can we do? Well, let's look at these 2 elements that have non-zero formal charges. And what we're going to do, let's fix them. And what I'm going to do is I'm going to take this second pair of electrons that forms the second bond, and I'm going to turn it into unshared electrons on fluorine. And now let's recalculate the formal charges. For boron, which as a free atom has 3 valence electrons, now this has 3 shared electrons. 3 minus 3 is 0. For this fluorine, it now has 6 unshared electrons and a shared one, that's 7, and fluorine likes to have 7, so 7 minus 7 is 0. So by just reducing the number of bonds that boron has and making it unshared on fluorine, what we've done is we have made this a much more stable atom from a formal charge point of view. All right, now we're going to talk about expanded octets, which is basically any time you have more than 8 electrons around an atom. And I will tell you that this exception to the octet rule is the most common exception. It actually occurs in many, many molecules. So this can happen for any element in row 3 or below. Why is that? Well, remember that you are going to put these paired electrons into an orbital. And the octet rule assumes that you have full s and full p orbitals. But once you get into the 3rd valence shell, we don't just have s and p orbitals like we did in 2. We now have d orbitals as well. And so it is possible to stash 1 or more extra pairs of electrons in those d orbitals. That's why it's possible. The next question is, why would it happen? Under what conditions? When do you use an expanded octet? Really, on 2 occasions. First, what if you are bonding 5 or 6 things to the central atom? Then there's no way you can have an octet. Second, it is possible that you may only be bonding 2, 3, or even 4 things to the central atom. But if you make some double bonds, so more than 4 bonds, that would actually help you with formal charge issues, the same way that making fewer bonds helped with formal charge issues for the incomplete octets. In both cases, when you're doing the math phase, the accounting steps, you're going to end up with weird answers if an expanded octet works. So what do I mean by weird answers? The best thing to do is to show you. So we're going to do 2 examples, one to illustrate each of these 2 potential reasons for using an expanded octet. And the first one we're going to tackle is SBF5, antimony pentafluoride. Here, antimony is the central atom. All 5 of the fluorines are bonded directly to it. I have to say that explicitly because people always say, well, what if one of the fluorines bonds to another fluorine? It does not happen that way. Okay, let's think about how our structure would go together. First, find the total number of valence electrons. Now, I've said before the math won't work, but even if you know the math is not going to work, even if you know that it's going to have to form more than 4 bonds, you always have to do step 1. So let's find the total number of valence electrons. Antimony has 5. Each of our 5 fluorines has 7, so that's going to give us a total of 35 from the fluorines. So 40 total valence electrons. Now let's figure out how many electrons we would need if we were going to give everything an octet. Antimony will want 8. Each of our 5 fluorines would want 8. That gives us a total of 48. How many shared electrons does our math tell us we need? 48 minus 40 is 8. That would be 4 bonds. And if you're thinking already about drawing this, you might realize that's a problem, but let me just show you that anyway. Let's write in antimony in the middle, and let's put all 5 fluorines around it. And let's start drawing our bonds. 1, 2, 3, 4, which is technically, according to the math, how many we need, but you see this is problematic because we really need 5 to bond that last fluorine. So 4 is the wrong number. So let's put in 5. Now we're going to distribute our unshared electrons, remembering that we actually did 5 bonds, not 4. And that means we had 10 shared electrons. So we started with 40 electrons. We used actually 10, not 8. So we have 30 left. And if you look at each of these fluorines, each of them has 2 shared electrons, which means they need 6 unshared electrons. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. And 6 times 5 is 30, so that is exactly the right number of electrons. So that is antimony pentafluoride. Again, it should have become fairly obvious to you, at least when you started drawing, if not when you saw the number of bonds or shared electrons, that the math was not working. Now we're going to draw a structure for xenon difluoride. Now people always give me weird looks when I bring up this compound. They're like, what? Noble gases do not form compounds. Well, they can. And if you think about it, the problem with noble gases is they have very high ionization energies. So if you want this to happen, you're going to need a noble gas that has a really low ionization energy for a noble gas. So you can tell that xenon would be one of these. And then you would want something that would pull really hard on those xenon electrons. And so something with a really high electronegativity would be great. And that's why we have a lot of noble gas fluorides and not many other compounds. Let's do XEF2. The total number of valence electrons, we're just going to start as we always do. Xenon has 8 valence electrons. We have 2 fluorines, each with 7, so that gives us 14, and so we therefore have 22. How many electrons do we need to complete our valence shells? Well, xenon needs 8. Each of our fluorines needs 8. That tells us 24. How many shared electrons? 2, which would be 1 bond, and you can see again, this just isn't going to work because you can't bond 2 fluorines with 1 xenon. So anytime you're not sure because the math doesn't work, just start drawing. Xenon and our 2 fluorines, let's give them each. 1 bond is not enough. We're going to need at least 2. And now let's distribute our unshared electrons. 22 minus actually 4, not 2. So that would be 18. And so 2, 4, 6 on the fluorine, 2, 4, 6 on this fluorine. That's 12 used so far. We still have 6 left. There's nowhere else to put them but on xenon. So xenon has 10 total electrons. Now, is there a better structure for xenon difluoride? Could you, for example, take these 2 electrons and make that a double bond? Well, we could take these unshared electrons and make them shared electrons. That would give us a double bond. But then look at this fluorine over here. It still has those 6 unshared electrons, and now it has 2 double bonds as well. So that's 10 total electrons on fluorine. And fluorine is in row 2. It can't have more than 8 electrons. So really, that is the structure for xenon difluoride. And then we can look at the formal charges on that. We know from previous experience that when you have 6 unshared electrons and 1 shared electron on fluorine, it gives it a 0 charge. And also the xenon has 2, 4, 6 unshared electrons, 2 bonds, that's 8 electrons. It normally has 8 valence electrons. So all of those have a 0. That is actually the best structure for xenon difluoride. It has to have an expanded octet on xenon. So there are many reasons why atoms might not obey the octet rule when they're forming covalent compounds. And as we get into the next video, you will start seeing why we especially look at that expanded octet as we're trying to determine the best structure for a compound. I hope this was helpful, and I look forward to seeing you again soon.